again as the talk gets going. It's a pleasure to have Lenka Zdeborova here today to speak. Just doing very brief introductions, but I couldn't help but notice that Lenka seems to definitely have her foot in two camps at different times of her life. So she got her PhD at both Prague and Paris, which two different schools at once. She's currently at EPFL in Switzerland. She just moved there this year, I understand. And she's a professor of physics and computer science. And before that, she was at CNRS at the Institute of Theoretical Physics. So we're really looking forward to hearing what she has to say about theoretical physics and satisfiability, and where the title, where the really hard problems really are. I don't have her title exactly in front of me, but so.
Right, that's the title. So thank you a lot, Sam. And let me go with the screen sharing. And that brings me to the slides that you should be seeing now. So I'm really glad to, have this half an hour or a bit more to discuss with you kind of my passion about the satisfiability problem in the workshop that is called 50 Years of Satisfiability, the Centrality of Sat in the Theory of Computation. So, you probably all know way more about Sat than I do, but nevertheless, I want to bring you maybe a slightly different perspective from what we learned about this problem in statistical physics. And I'm really sad that I cannot be with you in the beautiful building of the Calvin Lab in Berkeley. But at least I took the t-shirt. I'm wearing a t-shirt of one of the past programs just to have a bit of the Simons Institute atmosphere. So to start, despite the fact that my background and studies were in physics, the question that probably really fascinates me most in my research is, what are the problems that we can actually solve with a computer? So I think this is probably a common point with many of you. And, I will not be lecturing you about the theory of computation complexity, about which you know more than I do. So that's kind of the standard take on this. But we also all know that these days, even the NP hard problems are actually being solved in practice every day. And the kind of most, say, conjugated example these days is, of course, learning with neural networks, because there is many works. This is one of the first ones showing that even very simple works, neural networks with just 3 nodes are actually NP complete to train. Yet, we have this explosion of success with artificial intelligence these days. And it is fair to say that we are not close to have a theory that would actually explain why these problems that in the worst case are NP complete or NP hard are actually computationally tractable and doable. So that's, that brings me to the case of average case complexity, average over some natural distribution of instances. So, ideally we would like to average over the actual instances that come up in practice. But that we don't even know what that distribution actually is. So to approach it, we will be talking of some artificial distributions over instances. So I start with this historical note where, in 71, we have the concept of NP completeness coming to light by Cook. And then some years after that, there were a series of papers by Goldberg analyzing a random ensemble of the satisfiability problem, where you take n variables and m clauses, and then you include a variable in every clause. So you go through all the n times m pairs, and you include or not that variable in the clause with a given fixed probability. And this defines an ensemble, and this series of works analyze the Davis-Putnam algorithm for this SAT ensemble, and show that it is actually running on average in polynomial time and solves the problem. So this kind of brought, I was told, the community to hypothesize that maybe NP complete problems may be all on average easy. So that would have been interesting. But these 2 works in 91 and 92 kind of cut that statement wrong, because they introduced the kind of random k-sat ensemble, and the other paper, the analogous random coloring ensemble, that actually does not seem to be easy on average. So how is that one defined? So the only difference between the one of Goldberg is that in random k-sat, one actually fixes the number of variables that are present in every clause. So one has again n variables, m clauses, and one fixes a number k, in this case 3, and that's the number of variables per clause. And then for each, then one picks the variables at random for the clause, and for each of them at random, one decides whether they are negated or not. So this defines the random k-sat ensemble that I will be talking about. And the important quantity here will be the ratio between the number of clauses and the number of variables. And we will be looking at instances that are large, so have many clauses and many variables, but in such a way that this ratio is fixed to some constant. And so if you generate random k-sat instances this way, this brings us to this picture. So the x-axis here would be this alpha, this ratio, and the y-axis on the left is the probability that an instance generated this way is satisfiable, and you have the blue, green, and red line for bigger and bigger instances, and you see that that probability drops from 1 to 0, in a sharper and sharper way. And at the same time, for the same instances, what is plotted is the running time of the Davis-Putnam algorithm. That seems to be pretty small at small and large alpha, but it's kind of exploding around this threshold. So that's actually the running time of that algorithm is the other axis. So that brought the authors back in 91, 92 to the conjecture of sharp threshold, alpha S, that would exist in the random satisfiability problem, and the kind of realization that the hard instances might lie close to the threshold. So
Lenka, could I ask a question?
Yes, of course.
Yeah, I was wondering, you mentioned those are the running time of the Davis-Putnam algorithm. Do you know if that's the original Davis-Putnam algorithm where they resolve against all literals in all possible ways, one at a time, or is it maybe?
So yeah, so that's a figure that I took from a kind of popularization paper of Tom Hayes, and I don't remember which variant of the Davis-Putnam is run for this particular figure. But I mean, for the follow-up, it will not matter. And morally, I would believe that it should not matter. But okay, if it does, then I apologize. I don't remember.
No, I was just curious. Okay.
Yeah.
This is certainly not the CDCL algorithm, right? This is the DPLL. So this is not conflict-driven clause learning.
No, I believe there's
Okay.
Yeah.
But that's right. That's kind of just to report to these two papers from 91. So then we will be getting kind of to algorithms that actually run in polynomial time and whether they solve the problem or not. So to get there, I kind of jump 10 years forward and show you these two papers. That's kind of the ones where the statistical physics came into the game. So the one on the right was the first one, where this was a kind of a general discussion that this hardness can be related to the thresholds and to the phase transitions in physics. And the one that kind of really brought some wind into that subject is the one on the left by Mezar, Parisi, and Zekina, because that one actually not only had kind of a discussion that these are phase transitions and there might be related to hardness, but they actually had a very concrete computational, very concrete method to compute where the satisfiability threshold actually is. And they concluded that at this number there is an implicit formula. This number can be evaluated up to basically arbitrary precision. And next to it, they came up with the algorithm, the survey propagation algorithm, that actually solved instances of random instances of millions of variables up to this ratio alpha that was really, really close to this satisfiability threshold. So that back in the early 2000s was just not matched by any other solver. So that kind of brought maybe the computer science community to say, whoa, there is maybe something, since they have an algorithm that we do not have. So again, jumping a little bit forward, can we make these things more precise? And notably, can we discuss, where does the hardness actually come from? And again, okay, so that kind of goes back to my PhD thesis and this paper that we wrote back then. And this is the title page of my PhD thesis with this picture of kind of bubbles that I will go through in the next few slides. And I forgot to say that actually you had a few weeks ago a talk by Amin Koca-Oglan on the belief propagation and survey propagation. So, that's pretty much the same spirit. I'm like, all the results that I will be showing you are heavily using those same techniques. And I will not be really going through the details of the techniques, but rather discussing what they kind of tell us and what they lead us to conjecture about these problems. So let me start with that diagram. So these 6 panels are actually snapshots through different values of this alpha parameter. So 6 different values of the alpha parameter. And so each of these panels is kind of a picture of how the space of all possible satisfying assignment of the formula looks like. And you see that there are these bubbles, and some of them are blue and some of them are pink. The blue ones, there will be clusters with frozen variables, and I'm here defining what that means, and the pink ones without frozen variables. And these can be defined in various ways, and not for all of them we actually know rigorously that they're equivalent. But the kind of working definition that I like to think about is that one takes this belief propagation algorithm, which is an iterative procedure running on the factor graph corresponding to the satisfiability instance. And then one imaginarily, of course, imagines that one can initialize this belief propagation iterative algorithm in all possible satisfying assignments. So one is imagining there is like infinite, unlimited computational power, one can do that. And then one runs this belief propagation algorithm till convergence. It converges somewhere. And then one actually defines the clusters as equivalence classes of these belief propagation fixed points. So if from 2 satisfying assignments, I converge to the same fixed point, then I say that they are in the same cluster. And the frozen clusters are defined in the following way, that I initialize in a satisfying assignment and then I converge till a fixed point. So if from the initial assignment to the fixed point, finite fraction of the variables actually didn't move and stayed fixed to the original satisfying assignment, then I say that the cluster is frozen. And if all of them moved, then I say that, or almost all of them moved, then I say that this cluster is not frozen. And what the kind of method based on belief propagation and survey propagation allows us to do is actually analyze of how many of clusters of a given size. So size of a cluster will simply be the logarithm of the number of satisfying assignment that would belong to that cluster. So those methods allow us to analyze how many of those clusters there are, what are their sizes, and whether or not they are frozen or not. And as we are growing the number of clauses with respect to the number of variables, this parameter alpha, the properties of how these satisfying assignments are organized are changing. And I will be describing you 4 important changes on the way. So of course, this change where all satisfying assignments disappeared as the satisfiability threshold that, that has been conjectured and computed in this physics work. So that one is kind of clear what it should mean. But what are these 3, this clustering, condensation, and rigidity? So let me start with yes.
A quick question. What is the size of these formulas that you used?
What is the size?
Yeah, how many variables, how many clauses? Do you remember?
So these are not experiments. This is a closed form computation that is done in the limit when both the number of variables and this limit here. Where was it? This limit here, when n and m go to infinity and the ratio is fixed. And then the x-axis here, the x-axis is that ratio. Of course, here I don't have the numbers because the numbers then depend on k. And here I'm not even specifying k, but that axis is that ratio. And the calculation runs in the limit, in the high dimension limit. And so all these thresholds are sharp. So they happen at a very specific value of the alpha. So to get
if I could ask a question also, the point, these are clusters of truth assignments. So you're grouping truth assignments based on how the belief propagation algorithm converges in the end.
Yes.
Yes, okay.
Correct.
Okay. And the finite fraction of messages, that means the finite fraction of the variables keep their same value throughout the belief propagation algorithm. Is that's what frozen means?
That's the frozen ones. Yeah, that's what I call the frozen ones. And if finite fraction of them actually are frozen, then I color the cluster in blue and not in pink. And you can actually you can that's pretty easy to think that if you actually have frozen variables, you must have a decent fraction of them. It's not possible that you only have really small fraction of them, because they must create a kind of a backbone. So if you have them, you have bigger than some number of them that depends on the k and on the alpha.
Okay, good, thank you.
Other questions? Somebody was.
Yeah, but you have to know somehow that the formula is satisfying to begin with, or this.
So yes, so that's kind of in the satisfiability threshold conjecture or facts that with high probability these formulas are satisfiable. So this picture is true with high probability over the formulas. So if you pick a formula that is really big with high probability, this is what you will be getting. And for all the formulas with high probability will be behaving the same from, these thresholds will be the same, etc. They, the values of those thresholds all concentrate. So of course there will be exponentially rare instances, exponentially rare peaks where something entirely different is happening. So those I'm not describing in this calculation.
Okay, thank you.
So about the clustering threshold. So first of all, with our working definition of clusters, how do I define the clustering threshold? There's the smallest alpha at which actually the cluster that at the beginning, there is one cluster that contains almost all solutions. So maybe not all of them, but measure one of them. And when this large cluster actually breaks, that defines the clustering solution. So threshold, sorry. So beyond the clustering threshold, so below the clustering threshold, two random satisfying assignment will actually converge to the same BP fixed point. And above the above the clustering threshold, different satisfying assignments will actually lead to different BP fixed points. Not all of them, but that depends in which of the classes, other phases we will be. And I always kind of have a kind of geometric or static definition of what actually this threshold is, right? This is like about BP fixed point. This is not actually, it's kind of doesn't depend like on whether I'm able or not to solve the problem. But then these thresholds have actually algorithmic consequences. And all those algorithmic consequences, it's kind of the most interesting part here, but all of these are conjectures. So for instance, this clustering threshold, does it make the instance hard to solve? No, but it makes the instances hard to sample. So if I actually want to sample the satisfying assignments uniformly, and here the asterisk is actually in some pretty weak way that I just want quantities that concentrate to actually be the right ones, as what they would be on truly random assignment, then such sampling gets hard at this clustering threshold. So that's a precise conjecture that we believe stands. And there is, this paper is, for instance, one that provides some like pretty solid evidence towards this. But of course, I mean, we are, this is still conjecture, because at best one can hope to show that for a given class of algorithms. But we believe that this should be true for all sampling algorithms, polynomial ones, that actually at this threshold that gets hard, and below it is not hard. And
I have one question. This would mean that at this point, also approximate model counting would be infeasible, no? Because they
also counting would,
yeah.
So approximate again yes, but in a weaker sense than one usually thinks about approximate counting.
Okay.
Because in approximate in much weaker sense than what one actually usually, because even in this phase before the clustering, even the algorithms that are kind of sampling this big cluster, they will be missing the small ones. So one will be, so that's why this asterisk matters. So let me maybe say more precisely what this asterisk means. So imagine you had a randomly sampled solution, and that there is some quantity that is actually the same for almost every randomly sampled solution. So such as, for instance, in how many clauses are satisfied, say, by two variables. So what fraction of clauses are satisfied by two variables? So that's an example of a quantity that will concentrate. And so sampling being easy in this sense is that I can design an algorithm that will actually provide me solutions that are sufficiently random that these quantities will actually concentrate to the right value.
Okay, thank you.
Thank you for the question. So let's go to the second one, to the condensation. So that is again defined geometrically. That is a value of alpha above which, so I define overlap between two solutions sampled as random as simply their Hamming distance. And if I'm below the condensation threshold, then with high probability, if I pick two solutions, they will always have the same Hamming distance between them. And above the condensation threshold, this is not true. This Hamming distance between two randomly sampled solution will not actually be always the same number. It will be, in some fraction of instances, it will be of draws, it will be some number, it will have a non-trivial probability distribution. And another equivalent, although the equivalence might be hard to show, to prove, a definition of this condensation threshold is that the belief propagation is able to estimate how many satisfying assignments there are, but again, in a weaker sense, it's able to estimate the logarithm of their number divided by the size of the instance. And that is again some number of order 1, some constant, and that number is correctly estimated by the belief propagation below the condensation threshold and is not correctly estimated by the belief propagation above the condensation threshold. So that's in a sense a threshold below which the belief propagation counts the solution in some very weak sense and above which it doesn't. And the algorithmic consequence of this condensation threshold is pretty much nothing in particular. We have examples of other constraint satisfaction problems, such as the free coloring of random graphs, where simple algorithms provably work beyond the condensation threshold. So there is nothing really particular that this threshold means for algorithmic hardness of either sampling or finding the solutions. And this brings me to the third one, to the rigidity, that is defined as, that there are no more unfrozen clusters. So the rigidity threshold is the smallest alpha above which there are no more unfrozen clusters. And the algorithmic conjecture related to these frozen versus unfrozen clusters is pretty strong. So that's kind of based on evidence collected by all the algorithms that are actually able to solve these instances, including the survey propagation or local searches, all of them. They on large instances, they find solutions that belong to unfrozen clusters. So how do we check that? We simply initialize in that solution, and we see that the belief propagation converges to a fixed point where the variables are not frozen anymore. So this leads us to conjecture that it might be it seems like the frozen solutions are hard to find. Like none of the algorithms that are known that solve KSAT instances of, say, more than 10,000 variables actually find frozen solutions. So, and that's based on numerical evidence, but so far this conjecture stands. So that seems to be kind of related to the hardness of finding solutions, this rigidity threshold. But okay, is
just
that so?
Just to remind again, frozen clusters are one where the solutions have frozen variables, and the frozen variables meaning that it's like a backbone to a set of solutions. But what's the size? When do I say is there a minimum length for the backbone that you require?
Yes, so that's some fraction that is actually relatively big. Think 50% or 30% of the variables. This is because these instances, the alpha here is the average number of of clauses in which a variable is alpha times k. So that's typically something like 10. So it's the instance is pretty dense. So huge part of this instance is actually an expander. And if you actually should, how can it locally look like so that you can actually freeze variables so that, it cannot move, otherwise it would, unsatisfy some of its clauses, etc. So to actually to have such a chain of kind of constraints, you can see that this backbone needs to really take a large fraction of the instance. So this can be made precise, and this number will depend on the alpha and on the k, but it's actually not small. Think 30% or 50%, depending on, of course, the alpha and the k.
Thank
you. Okay. So here, just a little bit of a zoology, because here on the picture, I of course had one picture, so I put the clustering threshold first, and then the condensation, and then the rigidity, and then the satisfiability. So actually in random 3-SAT, the clustering and condensation thresholds are the same alpha, they are equal. And the rigidity threshold in the satisfiability in the 3-SAT is really close to the satisfiability threshold. It's actually, here I remind the conjecture for what is the satisfiability threshold from the physics works. And I also remind you that the survey propagation works up to really close to it. And from numerical evidence, the rigidity threshold is actually in between these numbers. So we have a paper on that back in 2008 or so. So it's really, really narrow, this region. But then when k is actually bigger than 3, so immediately the clustering and condensation threshold are actually strictly different. And as k is growing large, the clustering threshold and the clustering threshold is actually getting really far from both the condensation and satisfiability threshold. And the condensation and satisfiability threshold are actually close to each other, very close to each other at large k. And the rigidity threshold, for the k satisfiability, we don't actually know where it actually exactly is. That's harder to compute. But we do know that in a related problem. But before telling you about that, that kind of brings us back. So which of these thresholds actually indicate the hardness of finding the solutions? So far, maybe the rigidity threshold was closest, but actually not. So neither of them actually. So if we go now to a variant of the case satisfiability problem, the not all equal case sat problem, where we don't, well, it's all in the name, not all equal, is the meaning of the clauses. So that one, some of these analyses are simpler because of the symmetry that there is in the not all equal case set. So there we actually know how to analyze where the rigidity threshold is. And just these three numbers, like the clustering threshold within the not all equal case set is at this scaling here. Then the satisfiability is at 2 to the k minus 1k log 2. And then the rigidity threshold is about half. It's half of the satisfiable phase. But the clustering threshold is actually much lower than that factor, k times. And all the algorithms that we know how to, polynomial algorithms that we know how to analyze, including the survey propagation and all the algorithms derived from survey propagation, they actually all fail at about this scaling. So this leads us to a situation where the best known algorithms that we know how to analyze actually fail somewhere at the scaling that corresponds to the clustering threshold. Yet unfrozen variables exist much farther, actually up to half of the satisfiable phase. So this conjecture that frozen variables are hard to find, as I said, stands, but this case shows us that there is still a huge part of the satisfiable phase where unfrozen variables do exist, provably from non-constructive arguments, but we don't have algorithms that would be actually solving the problem. So that brings me to the conclusion that even on the level of being very conjectural, but wanting to be solid and wanting to provide you a number that somebody one day can prove, I do not know which number I should tell you if you ask me, which of these thresholds or which thresholds indicates the hardness, where's the onset of hardness of finding a solution in the random case set problem. We just don't know up to this day. So this is just a summary of this first part. So, okay, I should probably, I see that the time is running fast. So just to summarize kind of the timeline here. So in the 80s, we found we kind of had ensembles of case sets that were on average easy. Early 90s, people came up with the case set that seemed hard at the threshold. Then the early physics works conjectures that it is hard in a glassy kind of phase before the threshold. Then this has been made more precise and realized that it's maybe making the problem hard for sampling, but not for finding a solution. For finding a solution, the frozen solution seems to be hard to find, but we don't actually, that algorithms seem to stop actually before the unfrozen solutions all vanish. So that all means that in the random case set, we don't yet have a solid conjecture where the kind of hardness threshold on average is. But in some other problems, we actually do. And that's what I wanted to do in the second part of the talk. But Sam, tell me, I can take, yes, you can. How many minutes can I still take?
Oh, you can keep going. We've already had a lot of questions. So I think, let me see, you can go 10 to 15 minutes more is okay.
Okay, I will, okay, cool. So I have two instances of different ensembles of constraint satisfaction problems where we actually have a better idea of, or not a better, we have a conjecture that up to this date stands of where precisely the hardness actually starts. And so let me tell you about those two. So the first is the locked constraint satisfaction problems. So this is an idea that we had when we realized that is the freezing that is actually that might be making the instances hard. And we were kind of thinking, can we design an ensemble of constraint satisfaction problems where actually the freezing and clustering would be the same threshold? And the locked constraint satisfaction problems is exactly that ensemble. So let me tell you the definition. So I first will define occupational constraint satisfaction problems where each clause has k variables, and I forget about the negations. There are no negations. And now the constraints have the following role. They allow only a certain number. So now the occupied variables will be, say, the true ones, and the empty ones will be, say, the false ones. And the constraints, they allow only a certain number of occupied variables around them, and not 0 and not k. So it's not that everybody can be false. It's not that everybody can be true. So to give you an example, okay, and then let me say what locked will be, and then I give you the example. Locked occupation constraint satisfaction problem will be such that, in this table of integers that are allowed, there are no two consecutive integers that will be allowed. That's one requirement. And another requirement is that all variables are in at least two clauses. So there are no single variables that are not connected to any clause, and there are no leaves. There are no variables that are connected to only one clause. Everybody is at least in two clauses. And so just to show you, all possible occupation constraint satisfaction problems that can be defined this way for k = 4. So that would be the locked ones. One of them would be the 1 in 4 set. That would, the sum 0 is not allowed, 1 is not allowed, 2 is not allowed, say k - 1 is allowed. So this is rather k - 1 in k, or 1 in k, that's by symmetry the same. There will be also the 4 XOR set, where it is only the odd sums that are allowed and the even ones are not. There would be, for instance, the k in half in k set, or 2 in 4 set, where the 2 occupied variables are allowed and the rest is not allowed. And then the non-locked cases, that would be the not all equal set, or 1 or 2 in 4 set, where the 2 that are allowed are next to each other. So just to give you an example of this, like 1 or 3 in 5 set instance could look like this. And this would be one solution. Each clause has either 3 or 1 variable that is occupied. You can check. And that would be another solution. Again, each clause has either 3 or 1 variable that is occupied. And for these problems, as I said, the way we defined them was precisely to make the clustering threshold to be equal to the freezing threshold. As soon as clusters appear, they must have a backbone in these problems. Why? Because the way I define the locked, if you actually change one variable in a clause, you are forced to change at least one another. And since these graphs, because every variable is in at least two clauses, are expanders, we will have to change actually extensive number of variables. So all clusters must be frozen here. And again, we can compute the corresponding clustering or rigidity or freezing threshold, and they are all the same. And the satisfiability threshold is strictly different, bigger in these problems. And this time, when we actually try the kind of champions of the algorithms in random satisfiability, such as the survey propagation derived algorithms, which in this case become strictly the same algorithms as the belief propagation ones, we see for pretty large instances that the performance of the algorithms really drops sharply from 1 to 0 at this clustering equal rigidity threshold in these problems. So for these, and this would be another type of algorithms that do really well in random k-XOR set, but in these locked problems, they stop at the clustering threshold and don't work in this phase between the clustering and the satisfiability threshold. So So this is an ensemble of constraint satisfaction problems where the onset of the hardness of finding solutions is actually has a sharp conjecture and seems to stand up today. An interesting remark is that this conjecture that these locked CSPs are hard applies obviously only to the NP hard among them, because I show you that one of these locked problems was the XOR sat, the odd in 2K sat, if you want it in my setting. But that one is of course polynomial because it's a linear problem over the GF2. So, and that one is solved by Gaussian elimination. But it's actually a really bizarre case here, because for all these general purpose algorithms, this would be very hard to solve in the same sense that all the other ones are. So the Gaussian elimination stands as a kind of algorithm that is very kind of in a different class. So that was about the locked CSP. And then there are also the planted constraint satisfaction problems that, you know, the way I define planted constraint, so I will be talking of coloring because it's slightly easy to think about it than about the K-sat because of the non-symmetry in the K-sat. It's a bit more trickier. So those random instances, again, it's a different ensemble of random instances where you start with a solution and then you construct the instance so that that solution, so that that configuration is actually a solution. So you can start with the coloring of nodes and then you only put edges that are between nodes that have different color. You just don't put the edges that have the same color. So this way you define a planted constraint satisfaction problem. And in those, so those you can actually think of them as kind of paradigmatic examples of statistical inference problem. Instead of like finding any solution, you may actually want to ask, can I find something close to the solution that I started with? And that kind of diagram with bubbles also applies to these problems. And kind of the question whether we can or not find something that is close to the planted solution is actually one that has a sharply defined conjecture for where it becomes hard. And in the coloring problem, that actually yeah, I don't know. I mean, can I just go for 2 more minutes, or maybe we could leave the discussion? No, I'm a bit hesitant. I don't want to stretch it too much. You're muted, maybe?
I'm muted. No, please go ahead for a couple more minutes. It's fine. We started a little late and we've already had discussion. So,
yes. Yeah, I'm just okay. So here I'm back at my bubbles, and they're kind of very similar bubbles for the coloring problem, you know, clusters for the coloring problem. As for the K-sat problem, they really kind of are behaving very similarly when you analyze them from this point of view. And it's quite interesting that if I think about the planted ensemble of for the coloring problem, then actually for all that is below the condensation threshold, as I defined it before, the planted and the random ensemble are indistinguishable. They are actually information theoretically indistinguishable. So that's kind of interesting that the planted ensemble, that the planted solution is just one of the other solutions, and there is no way to actually find it. And it is after the condensation threshold that these two ensembles actually start to be different. And so after the condensation threshold, that if I didn't have kind of polynomial time restrictions, I would be able to find something close to the planted solution. But algorithmically, I am able to do so only much farther. And in the coloring, notably for large number of colors, the clustering is kind of at scaling of the average degree of the graph, that is a Q log Q. The condensation threshold is twice that. And the threshold above which the belief propagation is able to find something close to the planted coloring is Q squared. And here there is a conjecture that actually the belief that no polynomial algorithm can actually do a better job at finding the planted coloring than the belief propagation. And that, again, like said like that, it's a very bold conjecture, but nevertheless, it seems to be true. It seems to stand. You know, many people tried other algorithms, more powerful, other classes, and it's just not so far happening that other algorithms would be able to beat the belief propagation at this task. And again, here, that's a sharply defined transition. So for a long list, so for instance, here is an example of planted 5 coloring, where you need to go to average degree 16 for the belief propagation to work. And if the graph has average degree smaller than 16, then it's conjectured that no algorithm, polynomial one, will be able to find a correlation with the planted coloring, even though from information theory kind of non-constructive arguments, we know that with exponential algorithm, it would have been possible starting from something 13 point something. So much before 16. And there is this gap where no polynomial algorithms are so far known, which is, again, very sharply defined. Here, 16 is really 16. So if the graph is large and the average degree is smaller than 16, no way. If it is bigger than 16, belief propagation does a great job. This is kind of the correlation with the ground truth, what I'm plotting here. So this brings me kind of to this conjecture about the hard phase in, think planted ensembles of constraint satisfaction problems. But this actually generalizes to a very broad class of statistical inference problems, where there is a gap between what is information theoretically possible and what the belief propagation algorithm is achieving. And there is a big class of problems for which the belief propagation is conjectured to be optimal, in the sense that in the large size limit, no other polynomial algorithm so far is known that can do better. And this is just to show you just one slide on physics, that in these planted constraint satisfaction problems, that reason for the algorithmic hardness is kind of, from the physics point of view, exactly the same for which diamond actually is a diamond, because at normal pressure and normal temperature, diamond should be thermodynamically graphite. If it would actually turn into graphite, it would release a lot of heat, because it's energetically much happier as graphite at normal pressure and temperature, but it just never does so. It would do so in time that is longer than the age of the universe, so we don't really worry. And that's the same type of metastability close to a first order phase transition that is happening here in the diamond, as is happening in these Bayesian inference problems, such as the planted coloring. So that's kind of where, again, a bit of physics kicks in. And here's just a list of other inference problems where the exactly same origin of hard phase was analyzed and identified. So you have things like the clustering of networks and sparse principal component analysis and error correcting codes and generalized linear models, simple two-layer neural network, phase retrieval, and I mean, those of you working in various fields surely recognize some of these problems. And just to another Simons Institute program just next fall will be on exactly kind of these topics, the computational and gaps in these statistical inference problems. So this is the last slide, not completely last slide. The hard phase challenge is, if you can find a polynomial algorithm that would work at 0.99 times these conjecture thresholds, that would be amazing. But I believe that's not possible. And what can we do towards like proving something like this? Well, we definitely can work with classes of algorithms and prove that for certain classes of algorithms, this is not possible. And there is a lot of ongoing work in those directions. And that's kind of what that semester will be about. And that's the last slide, just to summarize. I showed you that in random KSAT, if you ask me where it is hard to sample, I know that's a clustering threshold. I can compute that one for you. If you ask me where finding a solution is hard, I honestly don't know, even on the level of kind of bold conjecture. For the random locked constraint satisfaction problem, so you can just think of these as a different ensemble of KSAT because all these are kind of mappable to KSAT. We do know where the hardness of finding a solution starts, at least on the conjecture level. And we also do know in the planted constraint satisfaction problems. And okay, that's all I wanted to tell you about, or kind of summarize.
Very good. Thank you very much. That was a great talk. Very happy to get it, and applaud on everyone's behalf since we can't do it properly. And we still have some time for questions. There's already one in the chat window, and we'll get to that in just a second. And I encourage everyone else to be thinking of your questions and either be ready to speak up or type it into the chat window. So Superteak asks, do you want me to read that for you? The notion of clustering and frozenness seems to be hinged on what happens in survey propagation / belief propagation. Why is this a natural way of defining clustering frozenness in the solution space? What other insights would be obtained if we use different notions of clustering, for example?
Yes, that's a very good question. So that kind of goes to the notion that the belief propagation is actually, and survey propagation is actually in some sense in the limit of large instances describing exactly what is happening in these random instances. So an alternative definition of clusters would be, instead of something more maybe less mysterious than belief propagation, imagine that you run a Monte Carlo Markov chain designed to sample the space of satisfying assignments, and that you initialize that Markov chain again in all possible solutions. And then you let the Markov chain run for time that is linear in the size of the system, not exponential. If you let it run exponential, then with a bit of like additional noise, you can prove that it will actually sample the space uniformly. But if you let it run for linear time, then what is the part of what is the subspace of the space of solutions it will actually sample close to uniformly? And those would exactly be the clusters again. Now, proving that what I just said is actually the same as what you get from the belief propagation fixed points is difficult. It's open. But that's the kind of conjecture behind why we use the belief propagation or survey propagation, because they are giving us an asymptotically exact description of how actually these Bayesian of attractions of something as natural as pretty much any detail balance Monte Carlo Markov chain look like. So this is why, and that's kind of where the exactness of these thresholds also come from. It comes from the conjecture that indeed the marginals that would be computed over these clusters are correctly captured by the belief propagation in the asymptotic limit when the instances are large.
Okay. So just to clarify that answer, if you define clusters using survey propagation instead of belief propagation, the notion of frozen variable or frozen cluster would be the same up in the limit, at least asymptotically.
Okay, sorry. So I define the clusters via the belief propagation. Now, okay, I should maybe say what's survey propagation. So survey propagation, in a sense, is if you defined now a new constraint satisfaction problem that is kind of living on the same factor graph, but the variables are not anymore the Boolean variables, but the variables now are the belief propagation messages. Then the belief propagation written on top of that belief propagation would be survey propagation. So it's a kind of belief propagation in a lifted space on the same factor graph. So I'm not really defining the clusters via the survey propagation. That would lead to a different notion of clusters if I had, say, like more levels of replica symmetry breaking. So I should not, you should not be thinking I define the clusters via the belief propagation point.
Okay, right.
The survey propagation is a different computational method to kind of analyze the properties of the clusters, if you want.
Okay, thank you. Maybe we have time for one more question, EJ?
Yeah, I had one I had a couple of questions. Thank you again for your very nice talk. One question was, I'm still having difficulty understanding why some of these threshold results would lift to say some other algorithm like stochastic local search, for example, right? Because stochastic local search algorithms are known to solve large random problems quite easily. So are you going to witness the same threshold behavior over there or not? That's
Yes,
one
that's the
question.
conjecture. So even either the local search algorithms will be weaker. In this case, their threshold can be, smaller, or they will. I mean, the conjecture is that the best they will achieve is the same threshold. So this is of course, that's precise. What you're kind of confused about. That's what like everybody is kind of confused. Nobody really knows, right, how to think about why would these thresholds actually have a meaning for other classes of algorithms. So for instance, there is a big line of work now about semi-definite programming algorithms, SOS, SDP type algorithms, SOS proofs. And these algorithms are doing something quite bizarre with the instances. They're in a sense projecting them into a different space, and yet they are finding exactly the same values for these thresholds. So there is probably something deeper happening here that we are just not understanding yet. Is just maybe that these methods from statistical physics based on belief propagation were kind of the first ones that were analyzed that discovered these thresholds. But my kind of guess would be that these thresholds actually have some deeper meaning beyond kind of defining them will a belief propagation, kind of deeper algorithmic meaning than that. But that's a wild kind of a conjecture.
Okay, just to follow up on that, has there been any work that you know of where people have used stochastic local search, kind of cross-verified this conjecture against stochastic local
Yes,
search
so you see, for
methods?
instance, I went too fast, right? But this, when I was trying to persuade you that these locked constraint satisfaction problems actually the algorithms stop at the threshold, so 3, close to 3 in this case. So here I was showing you the BP reinforcement algorithm. So that's kind of a BP used in a way that you can actually extract a satisfying assignment from it. And there was another graph that looked exactly almost the same, where I was actually using stochastic local search. One designed kind of to copy some of the stochastic local searches that are the best performing ones in random k-sat. So those work almost as well as the survey propagation, or say the same well. It's kind of it's kind of hard to say at the level of that numerics. One could say that the same, and here we are seeing the same thing. Both of them stop working at that threshold. So that's, for instance, one, that's from our paper in 2008, like one kind of numerical evidence that that's the case.
Can I ask one more question, Sam? Last?
Sure,
Yeah.
why not?
So any work on structured instances, threshold behavior for structured instances that you are aware of?
Structured in which way?
For example, the instances that are that come from verification application or software engineering and so on.
Yeah, so that's not much that I know of, or not anything that I know of. Maybe there are some that I don't know of. That's a very interesting question. Like in the context, my group is now kind of looking a lot at these like neural networks and the difference between like what happens for random IID data and what happens for the actual structured data is very kind of important and hot currently. And so kind of asking that same question in the SAT it's very interesting, but there is not much I know of.
Thank you very much. Thank you again.
Yeah, all right. Yeah, thank you for the talk again. That was great. We'll take about a 3-minute break just to give people a chance to stretch their legs. So we'll start promptly at 35 minutes past the hour. For me, that's 9:35 a.m. Thank you again, Lenka.
Thank you all. And if you have follow-up questions, just feel free to write me an email. I will be very happy to discuss whatever you were thinking about during the talk. Thank you.
Okay, good. And let's see, for Kian,